This video is about acceleration time graphs. You may have guessed by now that acceleration time graphs show an object's acceleration on the y-axis and the time on the x-axis. They're used to show complicated motion on a simple picture. For the next few units, we'll only be looking at situations with constant acceleration. So all of our acceleration graphs will be horizontal lines. It's pretty rare in physics to have non-constant acceleration. There's really only one or two places in the whole year where non-constant acceleration shows up. So for the foreseeable future, all the acceleration time graphs that we deal with will just be horizontal lines. So as an example, we can imagine this object that's accelerating at 3 meters per second for, let's say, 3 seconds. So on its speedometer, because it accelerated at 3 meters per second for 3 seconds, its final velocity at the end of that is going to be 9 meters per second. We can then imagine it decelerating at 2 meters per second for 2 seconds. I'm just kind of making up numbers here. Then at 1 meter per second for 3 seconds. And then at negative 1 meter per second for 4 seconds, like that. You may have guessed that an important property of acceleration time graphs is going to be the area under the curve. Again, that area is the area between the line of the graph and the x-axis. On acceleration time graphs, the area under the curve is going to be the change in velocity of the object over the time that has passed. So as an example, on this graph that I'm looking at here, this area is a rectangle and the height is acceleration and the base is the time. So the area is going to be the acceleration times the time, which if you plug that into the acceleration equation, you'll see is the change in velocity. Plugging this in, here that change in velocity is positive 15 meters per second. Plugging this in over here, I can see that this next area has a height of 1 and a base of 3, so that's going to be positive 3 meters per second. That next acceleration is just on the x-axis, so it doesn't have any change in velocity. And that makes sense because if the acceleration is staying at 0 and acceleration is a change in velocity over time, that means that there's no change in velocity over time. I can see that that last area is negative between the x-axis and the line of the graph, so that means that the area itself is going to be negative. The change in velocity will be negative 4 meters per second. So I can see that altogether, the total change in velocity on this graph is going to be positive 14 meters per second when I add these together. I'm going to go back to my example just to give you an intuition about the area under the curve of the acceleration time graph. So for the first 3 seconds, it's accelerating at 3 meters per second. And I can see that it went from 0 meters per second to 9 meters per second on the speedometer. And over here, I can see that this area is positive 9 meters per second. And that makes sense. It went from 0 to 9 meters per second, so the change is positive 9 meters per second. In this next part of the graph, the acceleration is negative 2 meters per second. So if I look at that area, I can see that that's negative 4 meters per second, and I can see that my velocity did change by negative 4 meters per second in that time. Next, it has an acceleration of positive 1 for 3 seconds, and again, I can see that the area is positive 3 meters per second, and it changed by positive 3 meters per second in that time. And finally, this is negative 1 meter per second for 4 seconds, and the velocity changed by the area, which is negative 4 meters per second, so it changed by negative 4 meters per second on my speedometer as well. We can translate from an acceleration time to a velocity time graph and vice versa. To translate from a velocity time to an acceleration time graph, we can use the fact that the slope on the velocity time graph is equal to the acceleration at that time. So I'm just going to section this off and find the slope at each point and call that the acceleration. In this first part, I can see that the slope is just positive 1 meter per second. In the second part, that's a flat line, so the slope there is going to be 0. In the third part of the graph, I can see that this is the run, this is the rise, so the slope is going to be negative 2 meters per second. And in the last part, this is the run, this is the rise, so the acceleration is positive 3 meters per second. I'm now going to draw all those numbers on my acceleration time graph. So the first part is a constant acceleration of 1. The second part is a constant acceleration of 0. The third is a constant acceleration of -2. And the last part is a constant acceleration of +3. So that's what the acceleration time graph would look like for that velocity time graph. There are two ways we can translate from an acceleration time to a velocity time graph. For both, we can start from any velocity on the velocity time graph because the acceleration time graph tells us nothing about the start velocity. So the first way I'm going to show you, this first example, is to use the fact that the acceleration is equal to the slope of the velocity graph. So we can just draw lines on the velocity time graph with the correct slopes based on the acceleration in each section of the acceleration time graph. So we can see that that first section over here is going to have an acceleration of 2, so that means that the slope of the velocity graph is going to be +2. So just drawing that line up 2 at a time, like this, for 3 seconds, gets me this line. In the second part, the acceleration is -1, so that means that the slope is going to be -1 for 5 seconds. For the third part, the acceleration is 0, so the slope is 0. And for the fourth part, the acceleration is +3, so that means that the slope is +3 for 2 seconds, like that. So that's one method we can use. The other method that we can use is finding the area under the curve and knowing that that's how much the velocity changes in that time. So I'm going to section this off again. And I'm going to find the area under the curve for each part of the acceleration time graph. So this first area is +6 meters per second, pretending here that the velocity starts at 0. I know that after 3 seconds, it's going to be rising by 6. So the next point on the graph will be over here. I can draw that connecting line, and that's what the first part of my graph looks like. The second part has an area under the curve of -5 meters per second. So I know I'm going to be going down 5 in that amount of time. So that's where the next point on my graph will appear. This next part has an acceleration of 0, so that means the slope is 0, so it's really just staying at the same velocity. In this last part, the area under the curve is +6 in 2 seconds, so that means that the velocity is going to change by +6 meters per second in 2 seconds. So that's the other way of translating from acceleration time graphs back to velocity time graphs.